Well, welcome to the late afternoon session. I'm a little tired, but I'm going to try to power through this, suffering from some jet lag. My name is Kevin Booth. I am currently an architect at FutureWay. I just joined, but for the 2 years before that, I was working on this OS in collaboration with some folks from FutureWay. I started this project as part of my PhD dissertation at Rice University back in Houston, Texas. Today I'm going to give a general overview of the operating system Theseus, which is a clean slate Rust native OS for safety and reliability. This is going to be, I think, a little bit different than some of the other talks in this session, right? Which, as I understand, have a heavy automotive focus. This is more of a hardcore OS talk. So if you have questions, feel free to interact. Feel free to interrupt me. Let me know if you're confused about anything, and we'll take it from there. All right. Let's get started. So in a nutshell, what is Theseus? So Theseus is a safe language operating system. So that means it runs everything in a single address space and a single privilege level. It's written entirely from scratch in Rust, right? So no C, no existing code, no POSIX, no Unix, none of that stuff. One of our design principles that we promote is something we term interlingual design, and that means within the language, so within Rust. That's why we call it a native Rust system. The goal here is to maximally empower or leverage the language in the compiler to the best of our ability, right? So that means unifying the view and the semantic understanding of resources between the OS runtime and the compiler, and then going beyond safety to do things like shift resource management processes into the compiler itself. So when this was a research operating system back at these universities, we had a few different goals. Things like the ability to do live evolution, right, which is arbitrarily change any component of the working OS at runtime without rebooting. Flexibility, where we could mix and match different components and kind of compose an OS out of all of these different crates. And then availability, which I think is probably most relevant towards today's topic, which is another way of saying reliability via a robust fault recovery mechanism. And I'll talk about that a little bit later on in the slides. So here's an intro. Here's an outline of the talk. First, I'll give an intro to what a safe language operating system is, since I'm sure a lot of folks are not familiar with that. I'll cover some other key principles of Theseus's design. And then I'll talk about some of our new directions, some of the more recent work on things like WebAssembly for safely executing legacy programs in unsafe languages. And I'll give a little bit of an overview of our support for lightweight formal verification, which is not yet published, but will be published actually a month from today. Yeah, October 23rd at a conference in Germany. And then I'll talk just one slide about ARC64 support. Okay, so by a show of hands, who knows what a safe language OS is? Anybody? No, okay. So basically, a safe language OS is one that uses language protection mechanisms instead of hardware, right, for isolation among different processes. Right, so all of the key components are written in a safe language. A lot of existing safe language operating systems have an unsafe language layer beneath the runtime. So, for example, the popular one was Singularity from Microsoft Research, and they had that was written in, I think, Sing Sharp, which is a dialect of C Sharp, a safe language, but they had a lot of unsafe C and C++ underneath it. So Theseus is not like that. Everything is in Rust. A safe language OS relies on language safety features to provide isolation between processes or tasks, whatever you want to call them, and to protect sensitive data or functionality from an entity that is considered unprivileged, right? As I mentioned up top, it forgoes or eschews hardware protection in some way. So what this means is that we either don't use the x86 model of different rings, like ring 0 and ring 3, or we run everything in a single address space. So Theseus actually does both. All right. So to give you a kind of a diagram representation of this, in a classic monolithic OS on the left side, we have something like Linux, Windows, or some hybrids of these types of systems where the whole kernel is a big monolithic chunk all in a single address space, and then each application process runs in its own address space. Microkernel takes this and moves some of that functionality, usually a lot of that functionality, into the user space as separate processes. And then those run in their own separate server processes or driver processes. And they have their own address space as well, and then applications run on top of that. A safe language OS like Theseus runs everything inside one single address space. So we have to make sure that we're doing everything right at the language level to protect these individual entities from one another. Oh, you can't see my cursor, but that's okay. So the key idea is that we want to leverage Rust's strong type system to prevent unintended behavior, right? So, I mean, this is probably something very familiar to most of you if you're familiar with Rust. The key distinction here is that we're enforcing this at compile time, not at runtime, so we're not relying on the hardware to enforce this, right? So there are some benefits of this and there are some disadvantages, right? So one of the benefits is efficiency. We don't have to switch between privilege levels or address spaces, which can be expensive, especially flushing page tables. Maybe you don't have to flush them all with modern TLB architectures, but you still have to pay some overhead penalty. One of the huge benefits is a simple programming model, right? So that allows you to view the entire OS as basically one big user space program. It makes things quite a bit simpler, like IPC. And then another, this is along the same lines as Rust as a whole. We want early detection of problems. We're removing things from a runtime error, a runtime failure like an assertion or a panic, into a compile time error. So we can catch it much earlier in the whole design and runtime process. There are some downsides. So the major downside is that you have to write everything in this safe language. And that's a little difficult. It's tedious. You can't freely incorporate legacy code without very careful consideration of what that code may be doing. For example, an untrusted C code base, right? And then there's also some minor penalty that you may or may not pay when you're using a safe language. For example, the overhead of bounds checking is something that people frequently cite. And there was a well-known project from, I believe, MIT where they were looking at doing this in Go, and they found that the overhead of Go's runtime bounds checks was like 4% or so. So it's definitely not free, but that balanced with the efficiency, you can still have a net positive. So why choose Rust, right? For me, personally, I was just interested in it. I first learned about it in 2017 at the Embedded Linux conference in Portland. And I was immediately enamored with Rust, very interested in it. But more importantly, for this particular case, it meets the needs of a safe language OS. And I've broken these into 3 categories. The first one is naming visibility, right? So this basically says that you cannot access private things, be it data, types, or functions that you can't name. So if you can't name it, you can't mess with it, you can't violate isolation. The second one is the ability to create capability-like objects, and we use this a lot with linear type systems and other substructural type systems like affine types, which is what Rust uses, sort of a slight variety of linear typing. What this says is basically you have to acquire an object or a reference to that object in order to invoke its methods or access its data, right? So you can't just arbitrarily, access random things via, pointer or virtual address dereferencing, right? That leads me into the third point, which is that we need the ability to classify whether or not something is unsafe. And I don't necessarily mean just in the sense of Rust's usage of the word unsafe, but something that could violate isolation, right? And then forbid that. So Rust lets us do that. Obviously, it has an unsafe keyword. So it's classifying that functionality for us already. But basically, we want to prevent the ability of the code that you're running in your trusted operating system environment from doing things like arbitrarily reinterpretively casting a type into another type, dereferencing pointers, something like that. Because if we allowed that, then that would that would make all of these rules from the above 2 points useless. Right? So we can't allow that. So let me give you a quick example. So Theseus has a page allocator. A page is a chunk of virtual memory. And I want to give a quick overview of how we leverage these properties of Rust to uphold safe language OS guarantees in the page allocator. So the first one, naming visibility. So typically this is the modifiers that you're used to seeing, public, private, whatever it may be, in your particular language of choice. This has to be enforced by the type system, right? So the compiler will tell you if you're invalidly accessing a private state, private field or something. For example, where's my cursor? For example, this pages here, right, that's private. So anybody out of this crate, outside of this domain of code, should not be able to access that, right? So the main way that you would allocate pages in Theseus is to call this function allocate pages at on the left. This is a significantly simplified version of the function, but basically you can optionally specify a virtual address that you want the allocated pages to start at. And then internally this will invoke a function called adjust chosen chunk, which is the way that we keep track of all of the metadata required to implement the actual allocator, right? So this will perform the logic. It will modify the internal fields of all of these different types that represent unallocated memory and allocated memory. And then it will return an allocated pages object, right? Only if it succeeds can you actually obtain an allocated pages object. And from there, you can use it to do something else. For example, map that to some allocated frames and then access that memory in a safe manner. But the point here is that all of these structs, and in some cases, the internal fields of the structs are private. So you couldn't allocate a page and then decide, hey, I'd like to make that page 5 pages bigger, so I'm going to just increment this pages field or something. You can't do that. All right, so that's pretty straightforward, I think. The second thing is capability-like objects, right? So in the same manner as what I just described, let's say that we have an application function, like func1 here, which is allocating some pages. If and only that function returns a successful result, can you actually use the pages, right? So that gives you the capability, the unique ability to access those pages. Whereas if you had something like a call to allocated pages that had already been taken, right? So let's say that func2 was called right after func1. Oh, right, you still can't see my cursor. Right, so let's say that func2 was invoked right after function 1. We've already allocated these pages, so we can't reallocate them, right? That invalidates the entire point of an allocator. So you'd get a failure, right? And at that point, you have an error. You don't have a capability to the allocated pages that you request, so you can't use them, right? And the way that we make sure that this works is, again, heavily simplified, but there's a free page list that basically is checked to make sure that those pages have not already been allocated. If they have been, then you cannot allocate them redundantly, right? And as I already sort of alluded to, the allocated pages type is one of several types needed to actually map memory. And only once you've mapped memory can you do something with it, right? Access it, write to it, something like that, right? So I have a very simple example here of some simplified code that would be used to map a frame buffer, right? So then we could draw something onto the screen. In this case, we're allocating, a series of 1024 pages and frames, mapping them together, right? Again, this is the question mark. Oh, you still can't see my cursor. This is the question mark operator, which is, an early return upon a failure. So if and only if we are able to successfully allocate pages and frames, can we proceed to mapping them, right? This makes sense. This is nothing too complicated, right? And then once we have pages and frames, this is required by this map memory function, right? It takes those by ownership. It treats them as the exclusive capability to that chunk of virtual memory and that chunk of physical memory, and then it returns an exclusive capability to that chunk of mapped virtual memory, which can then be used. I'll cover this a little bit more in more detail shortly. But then, basically, you're able to reinterpret this safely as, let's say, an array of pixels. And then you can go ahead and draw some whatever you want to the frame buffer. And then the third part of the safe language OS requirements is that you have to be able to forbid unsafety, right? So as I said earlier, if you are doing something like obtaining an allocated pages object and then trying to modify it, you can't do that because name invisibility prevents it, right? So this is ensured by Rust's type system and type checking. If we allowed unsafe code to work, if we allowed unsafe code to run, what we could do is just arbitrarily reinterpret this, right? We know the structure of it, we can guess it, perhaps we can hack the internal of it and modify some internal field, right? The problem is, this is an unsafe operation. So if we were banning unsafe code, which we do in applications that run directly on Theseus, you wouldn't be able to do this because doing this second to last line here requires unsafe code. We're dereferencing a raw pointer, right? Okay, and similarly, you can't just arbitrarily dereference pointers, right? So I can't just say, hey, give me some pointer to memory in the kernel, and I'm just going to print it, right? Can't do that. Okay, so that's kind of I think the difference between a safe language OS and regular operating systems, right? So that's why we need these abilities from Rust, and that's why we couldn't do something like this in C, right? C doesn't have this strong type system. If anything, it has a weak type system, which can catch some of these things, but it's not strictly forbidden. Okay, so that was a quick overview. Let me talk a little bit about what Theseus actually looks like and how we use some of these abilities to our benefit. So originally, Theseus was published in OSDI conference in 2020, and we had a few different design principles, some of which we've kept, some of which we have left behind. One of the things that we've kept is requiring runtime persistent bounds for all components. So what this means is that we have the system structure is a bunch of tiny components. They're all loaded dynamically at runtime, and then we can track their bounds with metadata, so we can know where all of these components are in memory throughout the entire execution of the system. Right? Another thing that we want to do, as I mentioned before, is really push this concept of interlingual design, or like Rust native system programming, such that we are enabling the compiler to check the rules of as many parts of the system as possible and semantically understand all of these different pieces of what's going on in the OS subsystems. We had some other things about state management, but I'm not going to talk about that today. We've kind of moved away from that. So the first principle was an OS structure of many tiny components, right? So each component is a cell. That's a unit of software-defined modularity. That's basically a fancy way of saying a crate, right? Currently, one cell is a crate. In the future, we may expand that definition to be things that aren't crates, for example, a WebAssembly component. But for now, just think of it as a single Rust crate, which is basically a set of code and data, and then the dependencies that that code or data has on other cells. These are elementary units of compilation. We want to keep them as small as possible for that reason. Generally, we don't use the Rust level mod keyword, the module keyword, except in specific isolated circumstances, and instead we try to promote them into their own distinct crates. Right? As I said already, all of these execute in a single address space at a single privilege level, right? But something unique to Theseus is that we actually do still use virtual addressing. So many safe language OSs run without an MMU. They run directly on physical addresses. I found that tedious and difficult. For example, if you wanted to allocate a huge chunk of memory, you can't really do that nicely if you can only access physical memory. So by using virtual memory, we can more easily obtain huge contiguous sections of memory. And it also gives us more efficient protection against stack overflow without paying the cost for something like segmented stacks, which is historically a very slow and expensive way to protect against stack overflow without memory protection. Right? What this gives you is a relatively minor distinction between an application component and a kernel component. They're basically the same thing, just that applications cannot use unsafe. Kernel crates can, but we generally avoid it as much as possible. Okay, so just to elaborate a little bit more on what a runtime persistent bound is, as I said, everything in the whole system is loaded and linked dynamically at runtime. That doesn't just mean drivers or loadable kernel modules or extensions or applications. That means everything, right? Because we do that, we're able to track all of the bounds. So we create kind of these metadata trees in memory, which show the dependency relationships at the section granularity, and also more clearly delineate the memory that each cell or crate, again, right, object, data, code, that kind of stuff, requires at runtime to actually exist, right? So these dependencies make it really easy to implement cell swapping, which is useful for live update and fault recovery. I'll show you that later on. But this is a really nice property of Theseus. What this gives you also is a view of these cells that is both consistent and complete, right? So that means at implementation time, when the developer is writing this, you see, a single crate, right? So we have this structure of a single crate. The cargo.toml manifest specifies the dependency, and the source folder contains all of its source and data, all of its code and data. And then we build that into a single object file. This is a raw, unlinked ELF file, right? So it's not something like a DLL or an SO or something. This is a raw.o file. So it's more akin to something like a Linux kernel module. And then at runtime, when we load it, we get this nice metadata tree, one per cell, right? And then the fact that everything runs in a single address space and privilege level provides this notion of completeness, right? Which is that every single component, no matter where it is across the system stack, is observable as a cell, right? So we can have this single mechanism where we load cells or swap cells or reload cells that have been corrupted for fault tolerance purposes, and we can apply that to anything that is loaded in Theseus. So you don't need something special for applications or libraries or kernel crates or drivers, right? They're all treated the same. Now, one thing, obviously you cannot run unlinked object files, right? So we have to do a little bit of bootstrapping to kind of finagle this this process where everything is dynamically linked and loaded, right? So what we do is we split the build process. We actually perform linkage, but we defer it until later. So as I said, everything's done at runtime, with the exception of the fully linked binary base image for the kernel, right? So that's something that you can actually load and run, like your bootloader, for example, Grub or something, can load this, or with a BIOS or UEFI or something on ARX64, you can load this, and then that jumps to the code that loads everything else, right? So it's a sort of a bootstrapping stage. So we term this the nano core because it's very small, right? It has a series of super minimal functionality. All it does is set up OS Bootstrap, takes over from the bootloader, sets up a very bare bones virtual memory subsystem so that we can actually load things. And then it includes the crate loading, which is effectively a linker and a loader that I implemented in Rust that runs within the core of the OS, right? So this is significantly smaller than what a microkernel is. So a lot of folks think of microkernels as like one of the smallest possible constructions for the OS core. But that's actually not true. You can get much further without including all of this different facades of functionality here. All right. Okay, so that was the first principle. The second principle, I think, is maybe the most important, which is what we call interlingual design. The idea here is to allow the Rust compiler to check and understand every part of the OS for us, such that it can catch errors as early as possible. And the way that we allow it to do so is by implementing things within the language's view model and semantic understanding of how things work. All right. So I know that's a little bit vague, but let me elaborate a little bit. So the compiler has an execution model, and what that means is every compiler expects the code that it generates to run in a certain way, right? So typically, this means it's expected to run as a single user space process, right? A single address space. There aren't many compilers, as far as I'm sure, where you can define something that runs in a different process and have that be a built-in code primitive, right? So we have to match the execution model that the compiler expects. So basically, this is a long way of saying single address space, single privilege level. That's what the compiler expects. And then, of course, in order to allow the compiler to semantically understand what all of our code is doing in the different subsystems of the OS, we need to remove those semantic gaps, right? So the first point, really the 0th point, because it's almost a given, is that we want to use and prioritize the usage of safe code over everything else, right? So over performance, over convenience, over ergonomics, right? In my experience, this actually has not been a problem. I think safety at the Rust level is actually quite easy to attain and make ergonomic and readable and performant. But I just wanted to get that out there. So the first main point of interlingual design is, first, we want to identify the invariants that we can use to prevent unsafe, incorrect usage of a resource, right? Again, I know this is a little bit high level, but we'll get to some examples in a second. What that means is using existing language level mechanisms to express the semantics of how that resource behaves and is used, right? So here's a concrete example. We use shared references, mutable references, ARC, right? Atomic reference count, RC, reference counted pointers, for safe aliasing instead of raw pointers, or instead of mapping multiple virtual pages to the same physical frame, right? Another thing that we do is use the type system to make invalid resource states completely unrepresentable, right? So this is things like the new type pattern, using very narrow trait bounds on functions and types, session types, type states, a bunch of these type techniques to make it impossible for you as a developer to write something that would be invalid for that given resource, right? What this enables the compiler to do is to subsume or take under its wing the OS's resource-specific invariants. So for example, if you're familiar with Rust, you already know that it has a pretty strong model of threads, stack memory, and heap memory, right? but it doesn't have a strong model of how this model-specific register in x86 works, right? It doesn't have a strong model of how all other arbitrary memory regions work in the OS, right? The OS knows and has deep semantic understanding of this stuff, but the Rust compiler doesn't. So our job here, our goal is to bridge that gap, unify the semantic understanding of the compiler and the OS, you, the developer of the OS subsystem, right? Another key point here is to preserve the language level context across interfaces. So that's a fancy way of saying use as high level of language types as you possibly can in all functions, right? So one counterexample of this would be something like invoking a system call, right? When you invoke a system call, you have to lower everything into raw primitive values, right? Typically just unsigned integers, and then reconstitute from those unsigned integers, typically pointer values, on the other side, on the kernel side, some higher level types, right? There's no guarantee that that correctness was preserved, right? So you have to do a lot of expensive checks, right? If we preserve the language level context, we don't have to do any of those checks. So, as a point here, we don't use system calls. There is something else that I like to promote about how Theseus works. It is not strictly unsafe to leak a resource in Rust, right? And I think that that's a key point. It makes reasoning about a lot of things much simpler, right? But it's bad, right? From an OS standpoint, it's bad to leak resources. So we want to prevent that. The way that we do that is by implementing a custom unwinder. So I took like a month or so to implement a dwarf, which is ELF's unwinding information format, a dwarf compatible unwinder from scratch, right? So this is completely independent of existing libraries like libunwind, which typically sit on top of an operating system, right? So, around the level of libc or something like that, right? What that means is that it works in all of the core OS runtime context, right? So we can even unwind in a CPU exception handler, which I don't think you'll find any other system that can do that. It also makes things a lot simpler, right? We don't have language-specific personalities. We don't have to register exception header frames. These are things that are very detailed, but basically add a lot of complexity into the world of unwinding. All right, it's much more flexible. We understand, this unwinder understands the unique structure of Theseus being composed of many tiny cells. And it's type safe, right? So this, I believe it's the first safe unwinder. We check landing pad addresses when we jump to them. So a landing pad is something like a drop handler, right? So you implement an arc, decrements the reference count when it's dropped. So we would jump to that when you're unwinding to make sure the reference counts get dropped, or unlocking a lock, or dropping an allocation, something like that, right? What this allows us to do is let the compiler drive resource management, right? Rather than the OS. So the developer merely has to define what happens, right, which is the drop handler in Rust. You implement that drop handler. The compiler is the one responsible for determining when that drop handler gets called. So this actually makes things way simpler, right? So we can ignore the significant complexity behind exceptional cleanup paths, which is a known hard problem. In tandem with that, this is sort of an extension of that last point, this relieves the OS from the burden of bookkeeping resources, right? So the application task or thread, right? You can think of it as a lightweight process, is able to bookkeep its own resources, right? By virtue of ownership. If you own a resource, then that is in use. Nobody else can use it. It's an exclusive capability to that resource unless you're explicitly sharing it. And it also gives you a flavor of sort of like protection from an untrusted OS, right? So the OS doesn't actually have the specific details of what that resource is or how to clean it up. It just knows that somebody else has acquired it, right? So this actually significantly simplifies state management. So I know that was dense. Let me give you some examples to hammer that home. Okay, so clearly the most important thing, in my opinion, that any OS can do is memory management, right? So some challenges with conventional memory management are that when you're mapping or remapping or unmapping something, you typically operate on virtual addresses, which is a handle to some underlying memory that the kernel is responsible for controlling, right? This introduces unsafety because there's a semantic gap between the OS level representation, right, which is this virtual address, and the language level understanding, which is a reference or a type or something like that, right? This causes what I call extralingual aliasing, which is aliasing beyond the language level, I gave some examples of that before, but one example here would be mapping multiple pages to the same frame. So that violates Rust's rule of aliasing XOR mutability, right? You can have one or the other, but not both at the same time, right? So our solution to this is an abstraction that I call mapped pages, right? So I think it's a pretty self-explanatory name. The idea here is that this bridges that semantic gap between the OS level and the Rust language level, right? And it allows Rust, the compiler, to apply its typical safety checks to all of those other non-heap, non-stack memory areas, right? So any arbitrary memory can be checked, right? So let me show you how that works. So here is a very simplified example of what the mapped pages struct looks like. We have a series of allocated pages. We have the flags with which it was mapped. That's like readable, writable, executable, stuff like that. Each mapped pages object represents a virtually contiguous memory region that is guaranteed to be mapped to real physical memory that is accessible under these flags permissions, right? So one invariant across the whole system, across the whole Theseus system, is that you cannot create invalid mappings and you can't create non-bijective mapping. A bijective mapping is just a fancy way of saying one-to-one, right? So you can't have two different pages mapped to the same frame. That would be non-bijective, okay? So if you take a look at the function signature of this map function, right, here we go, you can see, if you're familiar with Rust, it takes the allocated pages object and the allocated frames object by value, right? It consumes them. Right. What this means is after you call map with allocated pages and frames, you can no longer use them. These are not clonable. These are not copyable. They're true linear types. Right. We do all this logic. Again, this is significantly simplified, but it doesn't matter. The point is, it consumed the pages and frames, and that's what helps enforce that bijective mapping invariant. All right. So then let's say that we want to actually be able to access this memory, because what's the point of having memory if you can't do something with it, right? So looking at this code on the bottom left here, I don't know if you can see it, we have a function called asType. This is the way to overlay a sized, strongly typed object, like a struct, atop a region of untyped memory. This is a core OS primitive, right? So every OS has to do this. So what this does is it forbids you from taking ownership of an overlaid struct, which is a lossy action because you're disconnecting the existence of that struct from the lifetime of the underlying memory object that backs it, right? So I know that was complicated, but what I mean by that is we only return a reference. Okay, I can use my cursor. We only return a reference here to whatever type that we have overlaid on top of mapped pages, right? You cannot obtain a standalone owned instance of T here. That's just forbidden, right? So basically, you can only borrow the memory region as a particular type, right? And then, because the way the drop works, we're able to guarantee the fact that this memory mapping will always be mapped into the TLB and the page tables, while the owned object, that mapped page, actually exists, right? And then we also guarantee that it's automatically unmapped when you drop it, only once and exactly once when it is dropped. So this prevents things like use after free and double free. Okay, right, I covered that. Okay, so here's an example of how I might use it, right? So I have a struct called HPET registers, which is the high performance event timer, something like that. It's a common timer, right? So I'm using this as an example of how to access a hardware timer that works through MMIO using the mapped pages API. So I know that the HPET exists at this physical address. I obtain the frames for that. I obtain some pages. I map them. Oh, sorry, once again, you can't see. I obtain the frames. I obtain the pages. I map them. And then I'm able to reinterpretively cast or overlay this HPET register struct on top of that memory, right? And this is safe only because this is a plain old data type, right? POD, plain old data, right? It's just a bunch of integers, right? So in the previous slide, I didn't mention it, but there was this little trait bound here for T, meaning that it has to be safe to construct that purely from bytes. So that doesn't include things like a Rust reference, right? Like a shared reference or a mute reference, right? So there's a lot of other things like checking sizes, checking alignment in the asType function, but I'll skip that just to get at the key point, which is that this is how you can safely reinterpret memory, access it, and then if you wanted to do something more complicated with it, like let's say you wanted to have a shared memory region that multiple different entities or tasks are using, then you have to do it at the language level, right? It has to be aliasing intralingually, not extralingually, right? So you can do that with something like these two, language level reference types. Okay, so just to sum up, the mapped pages type enforces these invariants with the help of the compiler, right? So the invariants are that it's a bijective mapping, one-to-one between one virtual to physical frame. You can't access the memory beyond the bounds of that region, so you can't overlay a type that's bigger than the underlying memory region. We're guaranteed that the memory region gets to be unmapped exactly once, no more, no less. And then there's some other things that I didn't cover. But to sum up, mapped pages statically prevents invalid page faults, right? So you can never have a CPU exception for a page fault in Theseus at all. That's actually quite cool. So that speaks, I think, to the reliability notion of this session, right? If you know by construction at design time that you cannot have an invalid page fault, it makes your life a lot easier. Okay, so I think I covered some of this stuff, right? It applies, unifies the OS view and understanding of the system with the compiler's view. It applies this to all OS known resources, not just the stack and the heap, et cetera, et cetera. Okay, right. So let me talk a little bit about Theseus's fault recovery mechanism and how this works, right? So I use the word availability here. You can think of it as reliability, I guess, fault tolerance, whatever you want to call it. With the design that I gave based on safe Rust and intralingual design and implementation, we already get a lot of classes of faults statically preventable at compile time, right? So what I focus on here is transient hardware-induced faults that happen beneath the language level. So this is something that the compiler could never possibly account for, right? So think something like arbitrary bit corruption of memory, or like radiation hitting your memory, in a satellite, something like that, right? We take a cascading approach to fault recovery, and what that means is that we have a series of stages that are increasingly intrusive, right? So in the first case, what we do is just try to tolerate the fault. So we clean up the task, we run the unwinder, which, for example, if the task had acquired some locks, it releases those locks. What that allows the system to do is let other tasks proceed with making their own progress. And in many cases, that's enough, right? We don't have to do anything else, right? But in the case of a task that needs to be running all the time, we can go ahead and restart that task, right? So this allows us to respawn a new instance of that task, which again is like a thread or a process. And then if that isn't sufficient, then we can go ahead and completely reload, because as I mentioned before, everything's dynamically loaded at runtime. We can reload and relink in a fresh instance of that cell, and then redirect all of the references from the old cell that got corrupted to the new one, right? Something I want to highlight here is that these mechanisms for recovery have very, very few dependencies, right? So you can actually run them in a CPU exception handler, which is pretty strange. So here's just a quick and dirty diagram of how this might work. So let's say a fault happens, right? You had a random bit corruption occur that made you have an invalid instruction. So now we're in the CPU's exception handler for invalid opcode or something like that, right? We say, okay, where did that fault occur, right? Where's the instruction pointer that failed? We locate whatever cell that is in, right? Let's say the text section got corrupted, right? We load and link a fresh instance of that cell, replace the corrupted one, all right? And then we're using these live evolution features, which I didn't cover here, to basically swap in that cell to the new one, right? Right, okay, yeah, that's bottom left, so not great view. But what this can do is address corruption that happens in the content of a text section or a read-only data section. For data sections, stack and heap, things that are modifiable. This also covers things like TLS data and CPU local storage data. But for other things, we can take different approaches, but generally this is not applicable there. So I ran an experiment a while ago where I injected 800,000 faults of this kind of like spurious hardware malfunction variety. And I was able to get only around 660 to manifest. What that means is like the result of that fault actually caused a real problem, right? We ran quite a lot of varied workloads, rendering graphics to the screen, spawning tasks, accessing file systems, sending data between channels, right, which is kind of like IPC. And we made sure to target the working set of the memory that is actually being used by these cases, right? So we were able to successfully recover from just under 70% of these failures. And in general, a lot of the failures come from Rust's unfortunate lack of support for asynchronous unwinding, right? Not really Rust, just the LLVM compiler in general. What this means is that there's an unwinding table that tells you how to proceed if you get an exception at a certain instruction pointer. If that instruction pointer wasn't covered by the compiler's unwinding tables that it generates during build, we can't really do anything. We can look at the one next to it or the one before it or after it and try to use that as an approximation, but it doesn't always work, right? So even in these cases, there are still things we can do. We could, run a watchdog timer, a hardware watchdog timer that reboots, iteratively more chunks of the OS subsystems at a time, and try to, that could address like the hung tasks, right? That's a way to kill those off. But ultimately, you're never going to be able to recover from all faults, and that's just, kind of how things work. At least not without redundancy. Right, so I want to make the point that this is about reliability and availability without redundancy or replication, right? So within a single system. If you have multiple systems, like a satellite that NASA or any space agency runs, they have multiple different levels of redundancy. But, let's pretend that we don't have that, right? So as I mentioned, these fault recovery mechanisms have very few dependencies, which makes them really easy to run anywhere. And we can recover from a lot more faults than a typical microkernel system because these microkernels require a lot of other subsystems to actually work. Things like switching contexts, like task switching, moving to and from user space, right? Interrupts, IPC, all of these things need to work because of the structure inherent to a microkernel. Now, that's not to say that microkernels are bad. They can recover from some classes of faults that we can't. So just want to clarify that. So anyway, that's kind of a summary of what Theseus can do in terms of fault recovery. There's a lot more to be done here, but that's, I think, one of the easy things that we get for free by implementing some of these intralingual design decisions and having our own unwinder that can work anywhere. All right, so now I want to talk about some new directions that we've taken in the last 2 years. Some are more recent, some are older. And those are WebAssembly, formal verification, and support for other architectures. Yeah, I just said that. Okay. So if you recall, at the top of the presentation, I said, hey, how do you run legacy code in a safe language OS? Well, you can't, right? That's one of the major downsides. You can't be assured that legacy code in an unsafe language isn't going to violate the rules that you had that preserve isolation between different tasks. Right, so how do we overcome this? One modern solution is to use WebAssembly, right? So WebAssembly basically gets around this issue of the lack of isolation. Like if I were to just run C code directly on top of my Rust kernel, there would be no additional isolation. But WASM has a sandbox execution environment. So if you're not familiar with WebAssembly or WASM, basically it's a portable execution format, right? It has a very simple and clear machine model. You can I hesitate to say this, but you can sort of think of it like Java bytecode. It's just much better, and it's also language independent. So many different languages compile down to WebAssembly. Initially, it was designed for running on top of your web browser, but now it can be run on a whole host of systems, including embedded. So what this would allow us to do, the promise therein, is that we could take legacy code and run it safely in a WASM sandboxed environment on top of all of that Rust code that we had before. So I think this is a perfect fit for something like a single operator controlled environment where efficiency is important. Think automotive, think embedded, think functions as a service and the cloud backend. So it's really easy to actually use WASM. I just attended the WASM conference in Bellevue in Seattle 2 weeks ago, and there is so much work using this. It's extremely exciting. So you can build C on the left, you can build Rust on the right, and you can get basically the same WASM bytecode at the bottom, right? So that's a WASM module. Pretty much every major language supports this in their toolchain, including Rust, of course. Rust is one of the flagship languages that provides WASM support. And then you need some kind of WASM runtime to actually run it. This is akin to Java's JVM, right? So something like WASM time or WAMR, which is the WebAssembly micro runtime from Intel, or WASM Edge. There's so many different ones. You can take your pick. You can also run an interpreter, which is slower, but could be more accurate and more faithful to the spec or something. So what we wanted to do is move Theseus in a direction where it becomes a WASM native operating system. Basically, that's a fancy way of saying running WebAssembly on bare metal, right? Currently, Theseus can run WebAssembly in one of two ways. The first one, which I grayed out here because it's pretty terrible, is using a spec-compliant interpreter called WASM-I. That's a WASM interpreter. This works, and it's very easy to get running. It's actually no standard compatible, so you can take it and use it in your bare bones system. It's extremely slow, like hundreds of times slower than native code, right? So think the worst Python interpreter you've ever written. So that's not great. We can do better. So I spent 6 months, I think, porting WASM time to Theseus. And WASM time is a much more fully featured runtime that does both JIT and ahead of time compilation of WASM code. And then it also offers that runtime that can be that can take WASM modules and JIT or run them if they were already compiled ahead of time. We've also implemented WASI, which is the WebAssembly systems interface, and that's sort of like a POSIX-y system call set for accessing things like system timers and files, things like that, your environment variables. Some stuff we want to do in the future is to integrate the WASM component model with Theseus's model of cells or loaded crates. And the WASM component model is almost identical to this concept. It's basically a bit of code with dependencies, right? And it expresses these dependencies in terms of imports and exports, right? So kind of like an interface description language, right? We also want to support more robust WebAssembly interfaces like WebGPU for running complex rendering workloads in a WebAssembly engine, right? So in my view, this solves the classic problem that safe OSs have, which is legacy incompatibility, right? We have that sandbox execution model. Thanks to a lot of work, we can run it in a no standard environment. That means we can run it in the kernel itself, right? We can interop between WASM modules and native Rust code, and it makes it a lot easier to package up and then run a series of complex dependencies. Think of a large application with tons of libraries on top of a relatively immature operating system like Theseus. So just to give you an idea of what it took to get WASM time to run on no standard on Theseus, it took me, I think, about 6 months to get this to work, and it's probably pretty hard to see this, but I have a blog post that goes into this in great detail. All of the purple components here are things that I ported, all of the blue, purple and blue, and then the green components are the native Theseus provided features that we've mapped the WASM components onto, right? So all of these things are significantly complex, and then there's about maybe 6 or 7 key crates that make up the composition of WASM time itself. So what this allows us to do is run WASM modules side by side with native Rust crates compiled to native code, which is pretty cool. Something that we could do in the future is this is something that I would like to explore whenever I get time, is to take an existing device driver from another host operating system like Linux, compile that into WebAssembly, and run it on Theseus. There's a lot of complexity there. I won't get into it, but come talk to me about it after if you're interested in that. So just as a quick demo, I can give you some proof that this stuff works. I have a very simple test example up at the top, which is running in WASM time, and then a more complex example, which is a C++ calculator application called Exorbitant, which is running in the interpreter, right? So you can see these running, and that's proof that it works. So that's nice. Okay, so I've got, 10 minutes? Yeah, all right. So I have a little bit of time to talk about our newest work, which is lightweight formal verification approaches. This is a very research academic project right now. This is a collaboration with my colleagues at Yale. And the idea here is to prove some of these invariants that I had mentioned before, right? So I gave you a list of invariants for the mapped pages type, like it's guaranteed to be bijective. It's guaranteed to be dropped exactly once, so you prevent use after free and double free. It's guaranteed to not cause out of bounds accesses, right? However, importantly, that only holds if everything beneath it is actually implemented correctly, right? So in my initial paper, the way that I asserted that was just by manually checking, and we all know how flawed humans are, so that's never going to be perfect. Manually checking that all of these different conditions held, right? When those don't hold, for example, we had a very insidious, sneaky bug in our frame allocator that caused duplicate frames to be allocated accidentally. What this did is allowed you to violate that bijective mapping invariant to where we were able to have multiple pages mapped to the same frame. And then this caused very hard to debug spurious failures of DMA in a network driver, right? So this wasted, unfortunately, my colleagues' time for about a month until we discovered this bug. And this was the motivation to dig into a lightweight verification method for proving that these system invariants are actually correct and that they hold without the monstrous proof burden that you typically get associated with full system verification. So our key insight here is that the correctness of a high-level invariant, for example, bijective mapping, is modular, and it can be composed from a series of lower-level invariants that get carried forward through the type system. And most importantly, we can leverage Rust to help, the Rust compiler, to help ensure that those invariants are carried through types correctly, because it's type safe. So we adopt a hybrid proof architecture, and I'm not going to get into this in too much detail because it is not yet open sourced, but you can look for it in an upcoming conference, which I'll detail in a second. Basically, we want to maximize the use of linear type systems and interlingual design, basically relying on the compiler as much as we can, and then minimize the usage of everything else that requires a lot of manual effort, right? So things like full formal verification based on SMT solvers, structured prose proofs, and then of course manual checks, which we want to basically never do, right? You may ask, why do I call this lightweight, right? Well, there's a trade-off between the strength of the guarantee provided by this hybrid proof architecture and the proof effort, right? So it's significantly less effort, but it's also not as strong as full formal verification like you might see with SEL4 or something like that. So what this would look like for specifically the bijective mapping invariant, there's a lot of different composable things that all can be assembled together to give you this kind of proof diagram, right? So this is, again, massively simplified. But the purple sections here are things that we are enforcing by full formal verification, right? The white boxes are things that have invariants that have been proven, typically due to a combination of full formal verification, and the green boxes, which are invariants carried forward by the type system, right? So I don't think I have time to dig into this, but basically with a combination of all these techniques, we can write sort of a prose proof or a pictorial proof here that basically shows, proves that bijective mapping holds, so long as these formal verification guarantees also hold, right? So if you're wondering what kind of formal verification tool we use and how this might look, currently we're using Prusty, not sure how to say it. It's basically a SMT solver that allows you to do, the very typical pre and post conditions, right? So this is a simple function that we use in the frame allocator to see whether or not an existing range of frames that we're allocating overlaps with another one, right? So if we're freeing a series of frames, we're adding it back to the list. If we're adding a new series of frames that came from like a device driver and we needed to inform the frame allocator that this now exists, right? Think dynamically hot plug memory or something. This is the function that we would call. So there's a bunch of other functions involved, but you can see we have a series of conditions that the result, so the first condition, this big ensures block here says, if the result is false, these are the conditions that must hold. And then the latter two ensures blocks say, if the result is true, meaning there is an overlap, these are the conditions that should hold. So then this Prusty tool, right, can take these conditions and run it through the SMT solver, and we can get some formal guarantee about whether or not this function is correct and whether it actually does what it says it should. Again, correctness is hard. If you're familiar with the world of formal verification, you're not guaranteeing that it's correct. What you're guaranteeing is that your implementation matches the spec, right? So the spec is provided here by these blue attributes, and then the implementation is the Rust code below. So what we found using this hybrid proof architecture is that we can substantially reduce proof effort, right? So for the frame allocator, which is a few thousand lines of code, I think, and also the page allocator, they're very similar, we can get away with a spec and a proof that is under 200 lines of code. So that's a spec to implementation ratio of 3.2 to 1 and a proof to implementation ratio of only 1 to 73. So that's tiny, right? And the reason that we can do this is because we're relying on the type system, Rust, to extend that proof and spec to all of the other components that use these verified types, right? So in this case, allocated frames is the type that we're verifying. Anywhere that uses allocated frames, like the entire memory subsystem, right? All of that is then covered by that verification guarantee in just 200 lines of code. So if you want to compare this to other proof burdens, like Certicos and SAL4, typically we see things that are around 5 to 20 times larger than the size of the implementation, right? So in this case, we are significantly smaller than that. I also want to highlight that verification does not actually impose a performance penalty, and sometimes it can even be better. That really depends. I'm not going to cast this in a broad sense, but the key point here is that it actually makes things more maintainable, right? So a hybrid proof is a lot more maintainable because we're using the type system to take these invariants and make them applicable to a lot of other code. So as long as we don't change any code in the frame allocator, we don't need to re-verify anything. This is significantly different than an unsafe system like SAL4, where if you change something, anywhere in the microkernel, right, you need to go then and verify a bunch of other stuff. Now, Certicos and some other more recent fully verified operating systems have improved this modularity aspect of it, but we get it for free just by using type safety. So that's nice. So like I said, I don't have a lot of time to cover this, but this will be appearing in the workshop on kernel isolation, safety, and verification next month, exactly a month from today. So look out for that if you want more. Part of this is in the upstream Theseus repository, but not all of it. So I encourage you to be patient, and we will get it there as soon as I can. Okay, I'm out of time, so I will just give a really quick one-slide version of how Theseus works on ARIX64. Basically, the goal here was to allow Theseus to target embedded devices, right? So automotive, robotics, right? It's relevant there. Most of those are not x86, as you probably know. We spent quite a while, over 8 months with around 70 huge pull requests to make this work, and we can now run Theseus headlessly and remotely over serial or the network or whatever it is on ARIX64. We have yet to run it on any real hardware yet, but we plan to do that soon, the same hardware that OpenHarmony will run on, so that'll be exciting. I want to report some good news, which is that most of the abstractions that we had created for x86 held up, right? So I didn't have to make huge changes to the memory management subsystem other than the format of the page table entries. Tasking, also the same thing. You have different registers for context switching, but it's pretty much the same. Runtime loading and linking was almost entirely the same, with the exception of the relocation entries, which are different on ARIX64 and x86. But by far, our biggest challenges were supporting things like UEFI, because ARM, as far as I know, there's no legacy BIOS bootloader for ARIX64. And we needed a complete redesign of the interrupt subsystem and thread local storage and CPU local storage, which I'm very proud of how we got that to work. So if you want to know more about this, come chat with me and ask me about it. But for now, I'm going to go ahead and wrap up. So just to recap, Theseus has a series of rather unique design goals. We have a structure of many tiny cells where all of them are loaded and linked dynamically at runtime, which gives us the ability to see all of their bounds throughout all of execution. We really strive to leverage the language and empower the compiler to check all of the semantic and safety guarantees in an end-to-end, almost gapless manner, all the way from the very top applications to the low level of the kernel. And then, of course, we use our unwinder to shift resource bookkeeping and to prevent leakage, which is something that Rust safety alone does not do. Originally, I targeted things like reliability. We still do a little bit of this, but not so much. But our recent directions of WebAssembly and formal verification are going to bring some of this back into play. If you're curious how big Theseus is, it's not that big. It's around 80,000 lines of Rust and a few hundred lines of assembly. I just want to say that we're always looking for collaborators and contributors. It's fully open source. I no longer do this as my full-time job, but I did for the last couple of years. I spend about 20% of my time on it. We're very friendly, generally, on GitHub and Discord, so come chat with us. And if you're looking into formal verification or safe OS construction or Rust as a graduate study topic, I can easily get you in with the folks working on this at Yale.
Oh, yes.
I just want to acknowledge some work that other fine folks in this field have done. So I work with a few young guys from France and Australia, Nathan and Clem, as part of Theseus Systems. I have several collaborators who are now at Yale. And then, of course, the folks who sponsored the work for the last couple of years, my colleagues at FutureWay. So thanks very much, and if you have any questions, I'll be happy to take them, although I don't think we have time, but you can find me after. Thanks.